Okay, so we're in chapter 15, which is decision analysis. So, introduction here, we have business analytics is about making better decisions. And so decision analysis can be used to develop an optimal strategy. So when a decision maker is faced with several decision alternatives and an uncertain or risk-filled pattern of future events, and for example, the state of North Carolina used decision analysis in evaluating whether to implement a medical screening test to detect metabolic disorders in newborns. Now, a good decision analysis includes careful consideration of the risks. Risk analysis helps us to provide the probability information about the favorable as well as the unfavorable outcomes that may occur. Now, decision analysis considers problems that involve reasonably few decision alternatives and reasonably few possible future events. Now, the topics to be discussed under decision analysis are payoff tables and decision trees, sensitivity analysis, use of Bayes' theorem, and the first one that we're going to look at is problem formulation with payoff tables and decision trees. So problem formulation. So the first step in the decision analysis process is problem formulation. Now we're going to create verbal statements of the problem, and then we're going to identify the decision alternatives, the uncertain future events referred to as chance events, and the outcomes associated with each combination of decision alternative and chance event outcome. So for example, the construction project of Pittsburgh Development Corporation, the PDC as we're going to abbreviate it here, is commissioned preliminary architectural drawings for 3 different projects, one with 30 condominiums, one with 60, and one with 90. Now the financial success of the project depends on the size of the condominium complex and the chance event concerning the demand for the condominiums. Now, the statement of the PDC decision problem is to select the size of the new luxury condominium project that will lead to the largest profit given the uncertainty concerning the demand for the condominiums. And then given the statement of the problem, it is clear that the decision is to select the best size for the condominium complex. So the PDC has the following 3 decision alternatives. We have the D1, D2, and D3. D1 is a small complex with 30, D2 is a medium complex with 60 condominiums, and D3 is a large complex with 90. Now, in decision analysis, the possible outcomes for a chance event are the states of nature. Now, the states of nature are mutually exclusive, which means no more than one can occur, and they're collectively exhaustive, meaning at least one must occur. Thus, one and only one of the possible states of nature will occur. Now, for the PDC example, the chance event concerning the demand for the condominiums has 2 states in nature. S1, there's a strong demand for the condominiums, and S2, there's a weak demand. So we can formulate the problem here, and we're going to use payoff tables. Okay, and this is kind of out of your book here. We have the S1 is our strong demand, S2 is weak demand. We have our decision alternatives, small, medium, and large complexes. And so for the payoff table, the payoff is the outcome resulting from a specific combination of a decision alternative and a state of nature. Now, the payoff table is a table showing payoffs for all combinations of decision alternatives and states of nature. So for a small complex, D1, and strong demand, we have 8. That's going to be basically our payoff. And then we have 14, 20, 7, 5, and -9. And so those are all of our payoffs, okay? And these are in millions of dollars too, by the way. All right, so we're going to use the notation Vij to denote the payoff associated with the decision alternative I and state of nature J. And then using table 15.1, V31 equals 20. So V31 is 20, so it's 3, 1, so that's kind of how that works. And that indicates a payoff of $20 million occurs if the decision is to build a large complex and the strong demand state of nature occurs. Now we can make a decision tree. This provides a graphical representation of the decision-making process, shows the natural or logical progression that will occur over time. So for example, the topmost payoff of 8 indicates that $8 million profit is anticipated if the PDC constructs a small condominium complex, D1, and demand turns out to be strong, the S1. All right, so this is our decision tree. And so this is kind of how it goes. You know, if you had a small complex, you can even have a strong or a weak state. And so either you get 8 or 7. If you have the medium complex, then you can have a strong or weak state, 14 and 5. And then the large complex is either strong or weak, 20 or -9. And this correlates to the same values that are in this table here. It's just into a decision tree instead of the table, okay? So the decision tree here shows the 4 nodes numbered 1 through 4. So that's the 1, 2, 3, 4. Nodes are used to represent decisions and chance events. The square ones are used to depict the decision nodes. So you choose which one you're going to do, small, medium, or large. And the circles are to depict the chance nodes. And it's a chance that's strong or weak, basically, and through all the rest of them. That's all there are, chances strong or weak. So node 1 is a decision node, and nodes 2, 3, and 4 are the chance nodes. Now the branches connect the nodes, and those leaving the decision node correspond to the decision alternatives. The branches leaving each chance node correspond to the states of nature, so the S1 and S2. Now that, and then the other ones, the decision nodes, that's going to be the D1, D2, and D3. Now the outcomes or the payoffs are shown at the end of the states of nature branches. So kind of like, I guess you would say, the leaves out here. All right, so we can also do decision analysis without probabilities, optimistic approach, conservative approach, and the min-max regret approach. So decision analysis without probabilities is appropriate in situations in which a simple best case and worst case analysis is sufficient, and where the decision maker has little confidence in his or her ability to assess the probabilities. Now we have the optimistic approach. The optimistic approach evaluates each decision alternative in terms of the best payoff that can occur. Now the decision alternative that is recommended is the one that provides the best possible payoff. For minimization problems, this approach leads to choosing the alternative with the smallest payoff. Okay, so when you want minimization, you want the smallest payoff. All right, so here we have maximum payoff for each PDC decision alternative. So if we're looking at that, we want the maximum payoff, and so that's going to give us 20. That's going to be the maximum of the maximum payoff values, because that's going to be the state 1, basically, which is going to be the strongest value. So it's going to be the strongest, and so that's going to be our max payoff. So if the PDC problem, the optimistic approach would lead the decision maker to choose the alternative corresponding to the largest profit, which was the $20 million. Now, the conservative approach evaluates each decision alternative in terms of the worst payoff that can occur. Now, the decision alternative recommended is the one that provides the best of the worst possible payoffs. And for problems involving minimization, for example, when the output measure is cost, this approach identifies the alternative that will minimize the maximum payoff. Okay. So here, this is the minimum payoff. So now we're looking at the state 2, okay? And so what we want to do is, this is going to be the maximum of the minimum payoffs. And so that's going to be what this is. So that's going to be the D1 complex. And so for the PDC problem, the conservative approach would lead the decision maker to choose the alternative that maximizes the minimum possible profit that could be obtained, which is the state 2. Then we have the mini-max regret approach. Sometimes it's hard to say that one. All right, so the regret is the difference between the payoff associated with a particular decision alternative and the payoff associated with the decision that would yield the most desirable payoff for a given state of nature. Now, the regret is most often referred to as the opportunity loss. Under the mini-max regret approach, one would choose the decision alternative that minimizes the maximum state of regret that could occur over all possible states of nature, okay? All right, so here we're going to use equation 15.1, and so the Rij is equal to absolute value of Vj star minus Vij, and and it's also including the payoff tables in table 15.1, and the regret associated with each combination of decision alternatives Di and state of nature Sj is computed. Now, to compute the regret, subtract each entry in a column from the largest entry in the column. Now, Rij here is the regret associated with the decision alternative Di and state nature Sj. Vj star is the payoff value associated to the best decision for the state of nature Sj, and Vij is the payoff corresponding to decision alternative Di and state of nature Sj. Okay, so this is the decision tree for that, and I'm just putting this in here because this is kind of what we're going to be looking at, the boxes here. And so the opportunity loss or regret table for the PDC condominium project in millions of dollars. So what we're going to do is we're going to kind of look here, small complex, strong demand, S1 is going to give us 12, and what we're doing is we're subtracting. So again, what we're going to do is we're going to take the best decision for the state of nature Sj, so the one is going to be the strongest, so the highest one, 20. We're going to take 20 minus 8, which is 12, and that's what we get here. Then we're going to take 20 minus 14, and we're going to get 6, and then 20 minus 20 is going to give us 0. And then over here for the weak demand, that's when we go back here to 7, so that's the largest. So we take 7 minus 7 is 0, and then 7 minus 5 is 2, and 7 minus a minus 9 is going to give us the 16. And so that's how we get this column. And so what we're going to do now is the maximum regret for each PDC decision alternative. So that's 12, 6, and 16. Okay, so for the small complex, the largest is 12, the largest here is 6, and largest here is 16. And what we're going to do is we're going to take the minimum of the maximum regret. Okay, and so that would be the 6. So the next step in applying, and so now I'm going to kind of talk about it. The next step in applying the minimax regret and approach is to list the maximum regret for each decision alternative. And for the PDC problem, the alternative to construct the medium condominium complex with corresponding maximum regret of $6 million is the recommended minimax regret decision. And that's that point right there. And that's how we got it. We took these values, the ones in red, and for the weakest state we took that one minus the other two, and for the strong one we took that minus the other two. We got this table. Then we took the max of each of those rows, brought it here, then we took the minimum of those maximums as our mini-max value, and so that's going to be the maximum regret of $6 million. All right, so the decision analysis with probabilities, we're going to look at the expected value approach, the risk analysis, and then sensitivity analysis. So for the expected value approach, usually, again, we usually label that EV. Have a decision alternative is the sum of weighted payoffs for the decision alternative. Now, the weight for a payoff is the probability of the associated state of nature, and therefore the probability the payoff will occur. So the expected value of a decision alternative, DI, is just the sum of the probabilities times the V's. So what we have here. Now we're kind of back over here to our decision tree. And so now what we're doing is we're actually putting probabilities in here. So we have the probabilities for each of our states. So strong state gets a probability of 0.8, weak state gets a probability of 0.2. And what we can do is multiply 0.8 times 8, and then we add the 0.2 times the 7, and that will give us the expected value here for the small, which is 7.8. Then we do the same thing for this one, except we use the 14 and 5, and then the 20 and -9, and we can see all our different expected values. And this expected value is the highest, this is the lowest. So what we're going to do is select the decision branch leading to the chance node with the best expected value. So that was going to be the highest one, which is the D3. Now the decision alternative associated with this branch is the recommended decision. Now in practice, obtaining precise estimates of the probabilities for each state of nature is often impossible. So historical data is preferred to use for estimating the probabilities for the different states of nature, so those 0.8s and 0.2s. Now with risk analysis, this helps the decision maker recognize the difference between the expected value of a decision alternative and the payoff that may actually occur. Now the decision alternative and a state of nature combine to generate the payoff associated with a decision. Now the risk profile for decision alternatives shows the possible payoffs along with their associated probabilities. And this is kind of the risk profile for a large condominium complex, and so we can see our profits is going to be, down here -8 all the way up to the 20 here. So that's kind of our probabilities. And it's, probability 0.2, probability of the 0.8. Now, sensitivity analysis determines how changes in the probabilities for the states of nature or changes in the payoffs affect the recommended decision alternative. In many cases, the probabilities for the states of nature and the payoffs are based on subjective assessments. Sensitivity analysis helps the decision maker understand which of these inputs are critical to the choice of the best decision alternative. Now, if a small change in the value of one of the inputs causes a change in the recommended decision alternative, the solution to the decision analysis problem is sensitive to that particular input. So for example, suppose that the PDC problem, the probability for a strong demand is revised to 0.2 and the probability for a weak demand is revised to 0.8. Okay, so now we've got our expected values now are 7.2, 6.8, and 23.2. Now, with these probability assessments, the recommended decision alternative is to construct a small condominium complex with an expected value of 7.2 million. And when the probability of a strong demand is large, PDC should build the large complex. When the probability of strong demand is small, PDC should build the small complex. So depending on the probabilities, depending on which one they build, the large or the small. All right, decision analysis with sample information. So expected value of sample information and expected value of perfect information. So the decision makers have the ability to collect additional information about the states of nature. Additional information is obtained through experiments designed to provide sample information about the states of nature. Now, the preliminary or prior probability assessments for the states of nature that are the best probability values available prior to obtaining additional information. Then we have posterior probabilities or revised probabilities after obtaining additional information. Okay, so we have prior and posterior probabilities. So for example, the PDC management is considering a 6-month market research study designed to learn more about potential market acceptance of the PDC condominium project, anticipating 2 results. Favorable report, a substantial number of the individuals contacted express interest in purchasing a PDC condominium. An unfavorable report, very few of the individuals contacted express interest in purchasing a PDC condominium. So the decision tree, including the market research study, now is much more complex, as you can see here. So the study is here, and no study is here. And so this is what we saw initially down here. And now this is the part here when we start adding the market research study. So here, the favorable report gives us, again, we have our small, medium, large, and this is going to be our values up here, and then we have the unfavorable report, and then our values down here. And what we're going to do is come up with the probabilities. And so the probabilities now, so with the market study, favorable report, now it's going to be 0.94 for strong and 0.06 for the weak. So that's for the favorable. For the unfavorable, it's 0.35 for strong and 0.65 for the weak. And then again, we have the 0.8 and 0.2 for the no research. And it's just what the values there. So we can see that there's a big difference between favorable reports, unfavorable reports, and no research study at all. Okay. Then we can find out our expected values here as well. So we have expected values at the nodes 6 to 14. So we have 7.4, and all we're doing is we're taking, the 0.94 times this plus 0.06 times that, and then same thing here, all the way down. And so that gives us all of our expected values. We've seen these here, and so the new ones are the ones with the reports. And so now what we do is, this is the decision tree after choosing the best decision nodes at 3, 4, and 5, which are 3, 4, and 5 are right here, 3, 4, and 5. So we're choosing the best ones of these, and these. And as we can see, 18.26, 8.15, and 14.20. And if you want to see where that is on here, 18.26 is the max, so that was going to be the large. The 8.15 is the medium. And a 14.2, again, is the large, okay? All right, so now if we reduce that to 2 decision branches, we have the market study and the no market study, and that's going to be the 15.93 is the largest one. We're going to use that value, and 14.2 is going to be that one. So if the market research is favorable, we're going to construct the large condominium complex. If the market research is unfavorable, we're going to construct the medium condominium complex, okay? So expected value from sample information. So from figure 15.9, we can conclude that the difference, 15.93 minus the 14.20, is 1.73. And that's the expected value of the sample information, EVSI. Okay, so expected value of the with sample information, and then this is without the sample information, and so that's kind of the values here and what they're showing here, and you just take the absolute value. Now, expected value of perfect information. Now, a special case of gaining additional information related to a decision problem is when the sample information provides perfect information on the states of nature. Okay. So we can state PDC's optimal decision strategy when the perfect information becomes available as follows. If the state 1, select D3 and receive payoff of $20 million. If state 2, select D1 and receive a payoff of $7 million. And that's the perfect information thing. So that's the perfect, that would be what we choose, and that would what we'd be choosing, depending on if it's state 2 or state 1. Now, the original probabilities for the states of nature were 0.8 and 0.2. From equation 12.2, the expected value for the decision strategy that uses the perfect information is 0.8 times 20 plus 0.2 times 7, which is 17.4. So that's our expected value with perfect information. Earlier, we found the expected value approach is decision alternative D3 at 14.2 million. Now this is referred to as the expected value without perfect information. So now we have the expected value with and without perfect information, 17.4 versus 14.2. So example for this, expected value for the perfect information is 17.4 minus 14.2 is $3.2 million. And general expected value for perfect information is computed as, and again, just taking the with minus without and taking the absolute value, and that's the value there. All right, now we're going to go into something called Bayes' theorem. So we're going to compute branch probabilities with Bayes' theorem. All right, so Bayes' theorem can be used to compute branch probabilities for decision trees. The notion, just the bar is it's a vertical bar, but it's called given. So when you read it, it's like probability of state 1 given F is how it would be read, and this is probability of state 2 given F. And again, so it's the given, and it indicates a conditional probability. And the condition is, that's the probability of the state given that the F has already occurred, and this is given the S2 that F has already occurred. Because we're interested in the probability of a particular state of nature conditioned on the fact that we receive a favorable market report. So the probability of S1 given F and probability of S2 given F are referred to as posterior probabilities because they are conditional probabilities based on the outcome of the sample information. So F is a favorable market research report. U is an unfavorable market research report. S1 strong demand, state of nature 1, and S2 is weak demand, state of nature 2. And so this is going to be our PDC decision tree with all of this information here. So this is strong, this is weak, so this is the probability of S1 given it's F, which is favorable. And so those are going to be the favorable report. Now this is the unfavorable report, so this is going to be the probabilities of the different states given it's unfavorable, and then these are just going to be the probabilities of the states of nature. Okay, so these are going to be changing depending on if they're favorable or unfavorable. So in performing the probability computations, we need to know PDC's assessment of the probabilities of the two states of nature, PS1 and PS2. Now we must know the conditional probability of the market research outcomes given each state of nature. And then to carry out the probability calculations, we need the conditional probabilities for all sample outcomes given all states of nature. All right, so in the PDC problem, we assume that the following assessments are available for these conditional probabilities. So for favorable, this is unfavorable, this is our states of nature, strong and weak. So the probability of favorable, given it's a strong demand, is going to be 0.9. Given it's a favorable market research and it's a weak demand, that's 0.25. Now here, given its unfavorable market research and given its state of nature 1, that's 0.10. And for the unstable or unfavorable and state 2, that's going to be 0.75. So that's the conditional probabilities. And Bayes' theorem is stated as follows, and I'm not going to read it. It's just that's Bayes' theorem, and you just have to plug in all the values that we know. And so basically, you're going to have to plug in our values from all these items here, and that's going to get you what you need here for the Bayes' theorem. Okay. All right, so utility theory, utility and decision analysis, utility functions, and exponential utility function. All right, so when monetary value does not necessarily necessarily lead to the most preferred decision, expressing the value or the worth of a consequence in terms of its utility will permit the use of expected utility to identify the most desirable decision alternative. Now, utility is a measure of the total worth or relative desirability of a particular outcome, and this reflects the decision maker's attitude toward a collection of factors such as profit, loss, and risk. So examples of a situation in which utility can help in selecting the best decision alternative. We're going to use Swafford Inc. And it currently has 2 investment opportunities that require approximately the same cash outlay. Now, the cash requirements necessary prohibit Swafford from making more than one investment at a time. Consequently, there are 3 possible decision alternatives that can be considered. D1, we make the investment A, and that's what we're going to have here. D2, we're going to make investment B, and D3, we're not going to invest at all. And those are the 3 decision alternatives. Now we have 3 states of nature as well. Prices go up, that's basically the S1. Prices are stable, that's S2, and the prices go down, that's S3. And so that's the 3 states of nature, S1, S2, and S3. So utility and decision analysis. The decision maker who would choose a guaranteed payoff over a lottery with a superior expected payoff is a risk avoider. Okay, so that's going to be they want a guaranteed payoff over a lottery with a superior expected payoff. Now, the following steps state in general terms the procedure used to solve the Swafford investment problem. Step 1, we're going to develop the payoff table using monetary values. Step 2, then we're going to identify the best and the worst payoff values in the table and assign each a probability with U best payoff going to be greater than the U of the worst payoff. Okay. Step 3, for every other monetary value M in the original payoff table, do the following to determine its utility. So we're going to A, define the lottery such that there is a probability P of the best payoff and a probability of 1 minus P of the worst payoff. B, determine the value of P such that the decision maker is indifferent between a guaranteed payoff of M and the lottery defined in step 3A. And then C, calculate the utility of M as follows. Capital U of M equals P of U best payoff plus 1 minus P of U of worst payoff. Okay. Then we'll convert each monetary value in the payoff table to a utility. Then we're going to apply the expected utility approach to the utility table and that's developed in step 4 and select the decision alternative with the highest expected utility. And now we can compute this expected utility or the EU of the utilities in a similar fashion as we computed the expected values. It's just going to be the sum of the probability times the U. So it's just going to be multiplying the P of SI ij times the U of ij. Okay, and if we're going J from 1 to N, so depending on how many values of J you have, you go all the way to N. All right, so these are some examples of utility of monetary payoffs for Swafford Inc. So they give us the monetary value, then difference value of P, and so that's kind of the probabilities. It doesn't apply on the top and the bottom. Then we have the different probabilities here, and then this is going to be our utility values here. So the top one's going to be 10, the bottom one's going to be 0, and then we have the different values in between. And then we go to the utility table for Swafford Inc. And so for the investment A, which is your D1, the price is going up, that's going to be a 0.9 or 9.5. And now if we invest in B for D2, price is going up, that's going to be a 10. And do not invest, it's only going to be about a 7.5. And so, no monetary value there. It's going to be 0.75 basically straight across. So that's kind of why the bottom is 7.5 straight across. Now, if it's stable, then it's going to be 9, 5.5, and if the prices go down, it's going to be 0 and the 4.0. And again, that's in do not invest. So utility functions. Different decision makers may approach risk in terms of their assessment of utility. A risk taker is a decision maker who would choose a lottery over a guaranteed payoff when the expected value of the lottery is inferior to the guaranteed payoff. Actually, yeah. All right, so analyze the decision problem faced by Swafford from the point of view of a decision maker who would be classified as a risk taker. Compare the conservative approach of point of view for Swafford's president, a risk avoider, with the behavior of a decision maker who is a risk taker. All right, so now we're going to use revised utilities, assuming now we have a risk taker. So now we've basically changing our probabilities, and that's going to change our utility. Okay. Now the top still applies as far as the 0 and the 10, and because we're again not going to basically invest at this point, that's going to be the different value 0.25 and 2.5, and so basically those are going to be straight across zeros. Okay, so this is our payoff table. So if they invest D1, prices go up, that's going to be the 30. If they're stable, it's going to be the 20, and if they go down, that's going to be the minus 50. So that's going to be really bad there. D2 is going to be high, go up, it's going to be high, it's going to be good, it's going to be 50. If they're stable, you're going to lose 20, and if they go down, you're going to lose the 30. Okay. So using the state of nature probabilities, probability of state 1 is 0.3, probability of state 2 is 0.5, and probability of state 3 is 0.2. The expected utility for decision alternative is, well, we're just going to take that 0.3 times the 10, and then we're going to take the 0.5 times the 1.5, 0.2 times the 1.0, and this is for decision 2. Okay, and so that gives us 3.95, and that's when you add all those together after multiplying. Now, doing the same thing for D1 and D3, if we take the 0.3 times this, the 0.5 times that, and the 0.2 times that, we only end up with 3.5. Here, if we do the same thing for the bottom row, we end up only with 2.5. So we can see decision 2 is kind of the key. It has the highest expected utility here. And so the analysis recommends investment B with the highest expected utility of 3.95. Okay, so that's how we can use our utility table and probabilities to come up with which decision alternative to use. Now, the utility function for our risk avoider shows a diminishing marginal return for money. The utility function for a risk taker shows an increasing marginal return. Now, these values can be plotted on a graph on the next page as a utility function for money. The top curve is going to be the utility function for a risk avoider, and it's going to kind of show you where you're diminishing the marginal return. The bottom curve is the utility function for a risk taker, where you're going to increase the marginal return. And then we're at this middle line where the utility function for decision maker that's neutral to risk shows a constant return. Okay, so that's going to be our neutral constant return. This is going to be our risk taker because we're going to increase the monetary return from that neutral position. And here, this is going to be the risk avoider, where we're going to kind of lose the monetary return per that neutral risk taker here. So that kind of shows you how the avoider, the risk taker, and the neutral person would be. Now, the following characteristics are associated with a risk-neutral decision maker. The utility function can be drawn as a straight line connecting the best and the worst points. Now, the expected utility approach and the expected value approach applied to monetary payoffs result in the same action. So that's the key here with the risk-neutral decision makers. Now we have the exponential utility function. And so this is used as an alternative to assume that the decision maker's utility is defined when the decision maker provides enough indifference values to create a utility function. Now all the exponential utility functions indicate that the decision maker is risk adverse. So u of x equals 1 minus e to the minus x divided by r, and r is going to be our value that we really care about here. And this, the exponential utility function with different risk tolerances r values. These are our different r values. So lower value, this is kind of the curve you're looking at here, and then your r of 100 is kind of almost a straight line here. So the R parameter equation 15.7 represents, and that's just this value here, represents the decision maker's risk tolerance. It controls the shape of the exponential utility function. Larger values create flatter exponential functions, indicating the decision maker is less risk adverse, which is closer to the risk neutral. Now, smaller R values indicate the decision maker has less risk tolerance. Basically, they're more risk averse. So basically here, if the decision maker is comfortable accepting a gamble with 50% chance of winning $2,000 and a 50% chance of losing $1,000, but not with a gamble with a 50% chance of winning $3,000 and a 50% chance of losing $1,500, then we would use R as 2,000 in the equation. So if this is what they're more willing to do, then we would use R in the equation. And so that is all I have for this chapter. I hope this helps.